Hello students, I am Dr. S. Jyoti, Assistant Professor in Physics at Fatima College. Welcome to this e-content lecture for the physics students. In this video, we are going to learn about the optical fibers and to understand the behavior of light when it travels through different media, particularly the concepts of reflection, refraction, and total internal reflection. So these are the fundamental principles in optics and play an important role in many modern technologies such as optical fibers and communication systems. So let us now observe the animation and understand the physics behind it. We'll see. Optical fibers. Optical fibers are long, thin strands of very pure glass about the diameter of a human hair. They are arranged in bundles called optical cables and are used to transmit light signals over long distances. A single optical fiber consists of three layers, namely core, cladding, and buffer coating. Core is the thin glass center of the fiber through which the light travels. Cladding is the outer optical material surrounding the core that reflects the light back into the core. Buffer coating is the plastic coating that protects the fiber from moisture and from any kind of external damage. The bundles are protected by the cable's outer covering called a jacket. How does an optical fiber transmit light? Transmission of light through an optical fiber is similar to the transmission of light through a half wave. When you have to illuminate a long straight hallway, you just have to point the beam straight down the hallway as light rays always travel in a straight line. But to illuminate a hallway, which is a winding one with the multiple bends, you need to line the walls with the mirrors and angle the beam so that it bounces from side to side all along the hallway. This is exactly what happens in an optical fiber. Optical fibers make use of total internal reflection to confine the light within the core of the fiber. The core of the fiber optical has a higher refractive index than the cladding and hence the light suffers total internal reflection. Although the cladding does not carry light, it is nevertheless an essential part of the fiber. The cladding is not just a mere covering, it keeps the value of the critical angle constant throughout the whole length of the fiber. Then the propagation of light in an optical fiber. We will see about the propagation of light in an optical fiber. Let a ray of light be incident on the fiber, making an angle theta c with the axis as shown here. It gets refracted into the fiber. Let the refractor ray make an angle theta I at the core and the cladding interface. If theta I is greater than the critical angle theta C, then the ray suffers total internal reflection. So, all the energy in the ray of light is reflected into the core and none escapes into the cladding. The ray then crosses to the other side of the core, and because the fiber is more or less straight, the ray will meet the cladding on the other side at an angle, which again causes total internal reflection. The ray is then reflected across the core again in the same manner. In this way, the light zigzags its way along the fiber. Thus, the light gets transmitted to the end of the fiber. Because the cladding does not absorb any light from the core, the light wave can travel great distances. However, some of the light signal degrades within the fiber, mostly due to impurities in the glass. Then let us see the terminology used in fiber optics. Here you can see a ray of light traveling from air of refractive index mu0 into an optic fiber. The maximum angle of incidence in air for which all the incident ray is totally reflected at the interface of a pair of media having refractive indexes mu1 and mu2 is called the angle of acceptance. So, fiber attenuation, it is defined as the loss of light energy during its transmission through an optical fiber due to absorption by the impurities in the glass fiber. Then coming to the applications, optical fibers are used to transmit communication signals. In endoscope, used to investigate interior organs which cannot be viewed directly, and in photometers, the optical fibers are used. Fiber optic cables play a crucial role in our daily lives, connecting us to the internet and allowing us to enjoy services like video streaming, online gaming, and much more. These cables form the backbone of our global communication network, allowing information to be transmitted almost instantly around the world. To understand how fiber optics work, we first need to review some basic concepts. You have probably heard that the speed of light in a vacuum is approximately 300,000 kilometers per second. Every time this fact is mentioned, it is clarified that it is in a vacuum because light travels at other speeds when it passes through other media such as air, water, or glass. The ratio between the speed of light in a vacuum and the speed in the new medium is what is known as refractive index, and it is an intrinsic characteristics of each material. But the change in speed is not only the thing that occurs. When a light beam passes between two materials of different refractive indexes, its path is also affected. Similar to what happens when we try to see something in water, when the angle of incidence is small, the light beam undergoes a slight deflection as it passes from one material to other, a phenomenon known as refraction. However, when a critical angle is reached, the change in path is so great that the light can no longer pass through the other material. Understanding this, fiber optic cables are composed of three main layers: the core, the cladding, and the protective sheath. The core is a thin, transparent filament made up of glass or plastic. Surrounding the core is the cladding, which is also made up of glass or plastic, but with a different refractive index than the core. And finally, the protective sheath, an outer layer that protects fiber optic cables from physical and environmental damage, can be made up of materials such as plastic, Kevlar, or steel. In this way, when a beam of light enters the core, it will be reflected every time it reaches the edge with the cladding. Being guided along the cable for long distances, there are two main types of fiber optic cables: single mode fibers and multimode fibers. These differ in the size of their core and how they transmit light signals. Single mode fibers have a smaller core, usually around 9 micrometers in diameter. This allows light to travel in a single straight path with minimal signal loss, making them ideal for long distance transmission. Multimode fibers, on the other hand, have a larger core, usually around 50 to 60 micrometers in diameter. This allows them to transmit multiple light signals simultaneously, each taking a slightly different path. While this allows for higher data transfer rates, it can also cause signal degradation over long distances due to the different travel paths. As a result, multimode fibers are better suited for short range applications such as local area networks and data centers.